Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I'm going to continue with chapter number 3 and continue with the next topic, that is procedures. Till now we have covered 6 topics of chapter number 3, that is machine level representation of programs. Today I'm going to continue with chapter number 3 and the topic is 7, that is procedures. But before that, let's take a quick review of the last class, that is the Friday's class, what we have covered in the Friday's class. So let's start. In Friday's class, we have discussed what is control register, how we can use the control register, what is the behavior of a control register. So control register is a processor register, means it's a CPU register that is used to change the control, that is used to change the behavior of a CPU or other digital device. So control register is used for controlling the various modes of computer system. Various modes means there are multiple modes by which we can access the data. So control register helps in accessing the data, controlling the data, switching the addressing mode, paging control and coprocessor control. So control register stores all the controls or all the behaviors of a CPU so that controlling can be done in an easiest way. We have also covered what are the condition codes available. There are multiple condition codes available, 16 condition codes available, like CC, that is set CC, condition codes. So condition codes are basically a code that is used for giving the condition. These are the mnemonics. As I told you, mnemonics are used for writing the programs in assembly language. So conditions are the mnemonics that we can use in assembly language for writing the assembly language program. If the condition flag is true, then it's set to the 1, otherwise it is set to the 0. So we have studied multiple ways or multiple parts when it is set to 1 and when it is set to 0. It means condition codes. These are the multiple parts. If set E, that is condition is equal, this is the instruction, this is equal, then set F equals to 1. These are the multiple commands. Then set Z, that is 0, set F is equal to 1, set NE, that is not equal. This is NE means not equal, then the value is 0 because the not equal, so the output is false, that is denoted by 0. Then set NZ, that is not 0, it is also a 0. Set A, that is above 0, 0, 0, 0. There are so many conditions which we are using by which we can access, how we can access the data, how we can control the data. This is a not greater, this is less than or equals to, greater than equal, not less, neither greater nor equal, overflow, no overflow, sign, no sign, parity, parity even, no parity, parity odd. The CF means carry flag, ZF means zero flag, SF means sign flag, OF means overflow flag. So we have also discussed what is the meaning of carry flag, that is used to carry the most significant bit. As I told you, when we add two sign numbers, then if there is addition of 1 plus 1, that is 2. So 1 is carried to the, or 1 is carried over to the another number. That is your carry flag. That is done by the carry flag. Then there is a 0 flag. This is the most recent operation that gives the 0. Next, there is a sign flag that indicates the sign, whether it may be a positive, it may be a negative. So whenever we access or whenever we store the sign that is plus minus in register, that is stored by or that is done by the sign flag. Then there is a OF, that is overflow flag. So if there is an overflow in 2's complement or in 1 complement, so that is operated or that is stored by overflow flag. These are the multiple conditions which we have discussed in yesterday's class. There are generally 2 types of conditions, that is unconditional jump and conditional jump. As the name advises, unconditional jump means there is no condition on the basis of which we can jump. There is no condition, that is your unconditional jump. It does not follow the currently executing instruction. Means it jumps according to the in random. That is, if we follow the current instruction, if we follow a set of instruction, that it will be executed or it will re-execute the multiple steps. Then next one is your conditional jump. Basis on the condition, it is jumping from one place to another. Suppose my condition is that if the number is greater than 4, then it is jumped to a line 4. So it is your conditional jump. Means there is one condition, that is if 3 is greater than 4, then jump to the 4th line, otherwise jump to the 5th line. So this is your conditional jump. This says conditional execution in assembly language is accomplished by several looping and branching. Then we have also talked about what is CMP, that is compare instruction. This is nothing but it compares two operands. If two operands have a different value, so it compares whether the operand have a same value or have a multiple value. So CMP is used for comparing the two operands. Then this is a syntax for CMP, that is destination, source. So first of all destination, then source. So it compares, that is CMP compares destination to the source. This is the example. Then we have also discussed what is unconditional jump, that is done by the JMP, that is a jump operation or jump instruction. This is the syntax for jump, that is JMP label. Then we also talked about conditional jump in the last class. These are the examples of conditional jump. How we can jump from one place to another based on the conditions. There are multiple conditions or there are multiple instructions like JE, JZ, that is jump equal, jump 0. Then JNE, JNZ, that is jump not equal, jump not 0. Then there are multiple logical operations also, that is JE, Z. Then we have talked about in detail what is jump instruction, how we can use the jump instructions. This is a jump instruction that is used to or helps to implement instruction sequences that implement the control constructs of C. Control constructs means whenever we use the looping, branching, that is known as control constructs of C, like for, if else, do while. These are the control constructs. It means jump instruction also alters sequential execution. Then we have also studied what are the uses of IA32 with the help of jump instruction. These are the multiple flags, as I told you. This is the flags are set to 0 when it is true. Then we have also talked about conditional code flags. These are the multiple condition code flags, that is ZF, SF, sign flag, overflow flag. This is your 0 flag, this is your carry flag. These are the multiple instructions, these are the multiple synonyms, these are the multiple jump conditions, these are the description. This is your direct jump, indirect jump, equal 0, not equal not 0, less than equals to. Then we have also talked about some another instruction, that is your move instruction. So move instruction is nothing but it is a mnemonic that is used for copying the data from one location to another location. Suppose for example I have an operand A that have a value 10. I have to copy the operand A data, that is 10, to the operand B. So that is done by move instruction. And this move instruction can be of 8 bits, 16 bits, 32 bits or 64 bits if there is a x82 mode. So move instruction is used for copying the data from one part to the another part. One important thing is that it does not move the data from memory to memory, but it moves the data from memory to the register. This is the important point. I am repeating again. Move instruction does not move the data from memory to memory, but it moves the data from memory to register and register to memory. These are the multiple examples. These are the multiple example of register memory. This is, yeah, move memory to memory moves such as are not possible, because as I told you, there is a requirement for moving from memory to memory that is accomplished by the register. So first of all, convert this memory data or transfer this memory data to AX, that is your register. Then transfer the AX data to next memory. So indirectly these memories are swapped, but these are done by using the register, that is AX. So that's all for yesterday's session. This is what we have covered in the yesterday's class. Now let's start with the today's topic. Chapter number 3 continue, that is machine level representation of programs. So I'm going to start with topic procedures. This is your book. Till 6 topic I have covered, that is your conditional jumping, unconditional jumping. Today I'm going to start with topic number 7, that is procedures. So let's start with the procedures. A procedure is a collection of instructions. Means it is a group of instructions to which we can direct the flow of our program. Means on the basis of grouping of instruction, we can flow or we can direct the flow of our program. And once the execution of these instructions is over, means whenever there is a finish of these instructions, the task of these instructions are finished, control is again passed or back to the next line of process of the code, which calls on the procedure. Suppose, for example, I am writing the procedure after line number 4, that is in between 4 and 5. I am writing the code for procedure. So whenever we call the procedure, whenever we modify the procedure, whenever we run multiple commands, multiple instructions in the procedure, so after executing or after finishing the execution of the instruction, the control backs to the next instruction, that is your line number 5 as per my example. So procedure is a collection of instruction, means group of instruction, group of statements, by which we can direct the flow of our program. And once the execution, means whenever the task is done, that is execution of the instruction is done, then control is automatically passed or back to the next line of the process of the code, to which we can call the procedure. Means it back to the return of the place where we can start with the procedure. Procedure helps you to create legible and easy to modify programs. So these are used to modify the programs easily and very legible. Legible means very inefficient manner. At the time of invoking a procedure, so there is a requirement for invoking the procedure as well as calling the procedure. So whenever at the time of invoking a procedure, address of next instruction. As I told you, there is a PC. PC means whenever we use program counter, that stores the address for the next instruction. So at the time of invoking a procedure, the address of the next instruction of the program is kept on the stack. Stack is generally a memory or location where we can store the data. So that once the flow of program has been transferred and the procedure is done, one can return to the next line of the original program. As I told you, whenever we finish with the procedure, the control must be transferred to the program. So this says these instructions, these procedure instructions are carried out or kept onto the stack. Stack is the memory location in which we can store the data one by one. That uses LIFO, that is last in first out. Means whatever item comes last, that is come out at the first. That is your last in first term, LIFO. So all the instructions is kept on the stack so that once the flow of the program has been transferred or has been carried out and the procedure is done, means the program is done, flow is done, one can return to the next line of the original program, the one which called the procedure, so that it moves to the original program whenever it finishes the execution that is done by when we transfer or when we store the data in the stack. So this slide says what is procedure, how we can use the procedure, how we can invoke the procedure, and where we can store the procedure. Next, procedures or subroutine are very important. Procedure next name is or another name is subroutine. That is a part of the program. That is a set of instructions. So procedures or subroutines are very important in assembly language, as the assembly language programs tend to be large in size. As I told you, there is some function in function in C. As I told you, function is a sub part of the program. That is your block of the program, so that we can write or we can use multiple functions at multiple places in the program, and we can debug that functions very easily. In the same way, there are some procedures that is used in assembly language for dividing the main program or for dividing the whole program into multiple parts. Procedures are identified by a name, means procedure have a name. Following this name, the body of the procedure is described, which performs a well-defined job. Means whenever we follow the procedure, whenever we follow the name, the body of the procedure is described, which performs a well-defined job. Means the main task is that, or the main motto is that procedure have a name, and whenever we follow the procedure, this name will be accomplished, or the body of the procedure is described, which performs a well-defined job or which performs a specified task. And end of the procedure is indicated by a return statement. As I told you, in functions, that is returned by using the return statement. In the same way, procedures are also ended, or end of the procedure is indicated by the return statement. This is the syntax. This is the most important syntax. This is your procedure name. So first one is your procedure name. Then there is a procedure body. Body contains multiple parts or multiple lines. Then there is a return statement. I'm repeating again. This is the syntax for procedure. First one is your procedure name, then procedure body, and then there is a return statement. Procedure name means the name of the procedure. Then there will be a statement of the procedure, then there is a return statement. For example, if I am writing procedure name, that is procedure sample. This is your procedure name. Then there is a procedure body. This is used for writing the program. Then there is a return statement. So this is how we can write the procedure. So first of all, there is a procedure name, then there are multiple statements, then there is a return statement. This is how we can use the procedure. This is the syntax for procedure. Means first of all there is a procedure name, then procedure body, then there is a return statement. Next, continue with syntax of a procedure. There are two types of procedure. One is known as intra-segments and another is known as inter-segments. So intra-segment, which is found on the same segment of instruction, means which are found on the same level of instruction, and interstate segments means which can be stored on different memory segments. Same segment means that is stored on the same memory location, and intersegment means that is stored on different memory segment or different memory location. Suppose I'm using procedure. So I'm using two procedures. So that two procedures are stored on the same memory. For example, that are known as intra-segments. And if they are stored on multiple memory locations, that are known as intersegments. Right? So when the intersegment or the intra-segment procedures are used, the value of IP is known as IP Internet Protocol. IP is stored on the stack, and when the intra-segment are used, the value of CSIP is stored. Both here are intra-segment, the value of IP is stored, and when the intra-segment are used, the value of CSIP is stored. This is not your intra-segment, this is your intra-segment, this is your inter-segment. This is your wrong word, I will correct it. This is your inter-segment. So this is your intra-segment. So when the intra-segment procedures are used, the value of IP, that is Internet Protocol, is stored on the stack, and when inter-segment are used, the value of CSIP means along with the IP Internet Protocol, I will also give the name of computer system. So this is computer system, IP is stored. To divert the flow of a procedure, calling it the following directive is used. Means whenever we use the procedure, the following directive is used. Call name of the procedure, the part with which we can access. First one is your declaration. First one is your declaration. First one is your declaration part, then is your code part, then is your return statement, then termination of the procedure. These are the four parts as I told you in the last slide. First of all, declaration, name, then there is a code, then there is a return statement, then there is a termination statement. So these are the multiple parts how we can access or how we can use the procedure. So this slide is very important. This says there are two types of procedure, intra and inter. Intra means on the same segment, inter means on the different memory segments. When intra segment is used, the value of only IP, that is Internet Protocol, is stored on the stack. But when inter segment are used, the value of CSIP, that is Computer System IP, is stored. For example, now there is an example. If I want to routine which add 2 bytes stored in H and AL. H is also a register, AL is also a register, and kept the addition in BX register. Means these are the two registers. We can add the 2 bytes and store the addition in BX register. So this is your procedure. Adding probe, that is procedure near. So the name of the procedure is near. Declaration of the procedure. This is your comment. This part is your comment part, and this is your procedure name. Right. Then move BX to 0 to BX. This is your source. This is your destination. So put 0 to register BX. This is content of the procedure. These are the comments for user friendliness. So these are the comments available for your understanding. Then move AH to B1. This is also a content, move to B1. Now move 0 to AH. Now AH has a value 0. Now add BX and AX. First of all, AX has a value 0, right? BX has a value 0 and AX, this is not a value 0. Now put AX into the BX. Then there is a return. This is a return directive. This is how we can use the procedure. These are the examples stored in AH and AL, and we can use for the addition that is stored in BX register. Then add NP, that is end of the procedure declaration. That is your add NP. This is how we can use the procedures. This says On the declaration of the first word, adding correspond to the name of our procedure. Probe clear it as and the word near indicates the MASM that the procedure is intra-segment. So near indicates that this is your intra-segment, means these are stored on the same segment location. That is your intra-segment. Next, return RET. RET directive loads the IP address stored on the stack to return to the original program. Lastly, the add operation. Lastly, the add NP directive indicates the end of the procedure. These are the multiple syntax, multiple parts of a procedure. Next is your same procedures. Procedures are very important for writing reusable and maintainable code. As I told you in C, functions are used for writing the reusable code. In the same way, procedures are used or very important for writing reusable and maintainable code in assembly and high-level language. And how they are implemented? They are implemented by using four methods. First one is your application binary interfaces, that is ABI, then calling conventions, recursive calls, and then there is an example. These are the general concepts which we can use in procedures. One is your caller, that is the calling procedure, where we have to call the procedure. Then there is a callee, the procedure called by the caller. Means first of all we call the function, we call the procedure, that is known as caller, and to whom we can call the procedure, that is known as callee. That is CALLEE, callee. This is your int multiply xy, return x into y, product equals to mul AB. So this is how we can jump from one location to another location. So whenever the function, the language uses this line, that is product equals to mul AB. So this directly jump the cursor to this point, that is int multiply xy, then return x into y. This says caller and callee must agree on how to pass the parameter. These are the parameters AB and XY. How to return the statement. This is your return procedure, that is return x into y. How to maintain relevant information across code. Means how to transfer the data from one part to the another part. So this is the basic concept of procedures. How we can use the procedures. So this is a procedure. Next one is your stack frame structure. As I told you, there is a stack. We can store the data. Stack follows LIFO, that is last in first out. Means whenever whatever we put in the last item, that will be inserted or that will be deleted first, or that will be pop up first. So inserting the data is known as push in stack, and deleting the data or removing the data is known as pop in the stack. This says IE32 programs make use of the program stack to support procedure code. This is the portion of the stack. This is known as stack frame. There is a diagram. This is a diagram, frame structure. As I told you, stack. This is your stack. First of all, there is the argument build area. This is your saved register, local variables, saved EBP, return address, argument 1 up to argument n, and these are the multiple stack items. This is a stack bottom. Means first of all, we can delete the data or we can pop the data from the deleted or from the bottom of the stack. This is stack pointer can move while the procedure is executing, and hence most important information or most information is accessed relative to the frame pointer. Sometimes procedure P, the caller calls Q. This is your P and Q. For example, the argument to P and Q are contained within the stack frame for P. So these are the multiple examples. This is EBP and ESP. This is procedure Q. Procedure Q is your calling function or your called function. This is your calling function and this is your caller function. Means P calls to the procedure Q. So P becomes your caller and Q becomes your calling. This is procedure Q also uses the stack for any local variable that cannot be stored in registers. This can occur due to the following reasons. First, there are no enough registers to hold all of the local data. Some of the local data which are used as array or structures and hence must be accessed by array or structure references. The address operator is applied to a local variable. As I told you, there is a address operator, that is your ampersand operator. So we can access or we can write the procedure by the calling function with the use of these registers, that is your ampersand register. Next topic is your transferring control, means how to transfer the control from one part to another part. This is the instructions supporting procedure calls and returns are shown in the following table. These are the multiple procedure calls. As I told you, there are two concepts, caller and calling. This is a call, label, procedure call, ampersand operand, this is procedure call, leave, prepare stack for return, RET, return for call. These are the multiple transfer controls which we are using in assembly language program. The call instruction has a target indicating the address of the instruction where the called procedure starts. So the call function is indicating the address from where the call function starts. Like jumps, so we are jumping, a call can either be direct or indirect. So we can jump the call from in the assembly either in a direct way or in indirect way. In assembly code, the target of a direct call is given as a label, while the target of indirect call is given by a asterisk followed by a operand. So this is your direct call, this is your indirect call. The effect of a call instruction is to push. As I told you, there is whenever we insert into the stack, that is known as push. So the effect is to push a return address on the stack and jump to the start of the called procedure. Means whenever we call the instruction, that is pushed into the stack or that is jumped into the stack and then jump to the start of the called procedure. For example, if I have a function that I will be calling a procedure, then automatically my cursor or my pointer moves to the called function at the starting phase where we can store the or where we can access the or where we can start the called procedure. So that execution will resume at this location when the called procedure returns. The RET instruction pops. As I told you, there is a pop operation whenever we delete the data. So whenever we return from the procedure, the return instruction, that is your RET instruction, pops an address of the stack, means remove the address from the stack and jump to this location. This whole paragraph simply explains how to call the function from calling function to called function and how to return back to the calling function. This is your example. First is your executing call, that is after call, that is after RET, return. This is your example, call next, next, pop1, ampersand, EAX. Next, register usage convention, means how to use the register or how to use multiple registers whenever we use register usage convention. So how we can store the data of the called function and calling function in the register. So this is the main target or this is the main topic of register usage convention. So let's see in PPTs. This is your register usage convention. Rules about what gets to use save which registers. This is the caller save. R0, R3, R12 means it is from R3 to R12. Then there is a LR, CTR control, CR0. These are your caller save. Then there is a callee save, that is your R14 to R31, CR24, non-volatile registers where values can be preserved across code and must be restored by callee before returning to the caller. These are the multiple registers which we are using whenever we use the procedure for writing the assembly language program. So first one is your caller save, that is your caller register, then is your callee save, that is your callee register. There are three dedicated registers, that is R1, R2 and R13. So these are the registers on the which we can use or we can store the procedures, caller function, callee function and the return function. So this says the set of program registers acts as a single resource shared by all of the procedures. Although only one procedure can be active or active at a given time, make sure that one procedure, that is one caller, calls another, that is callee. The callee does not override some register value. So this says only one register, only one input or the one output can be stored in the calling function or in the register. No function can override the another function. This is your example. This is your int p, int x. This is your function. The function return type is int and the function name is p. These are the arguments. Means only one example or the one argument is used. This is int y equals to x into x. This is another variable declare that stores x into x, means square of x. Then z equals to q y. This is your function. So this is how we can use the procedures. This is your function. Then return y plus z. But z have a value that gives the function, that gives the procedure qy. So this is your calling function, that is qy is the procedure name or calling function. This line is your calling function. So first of all, y have a value, z have a value, then return y plus z. So adding y plus z value. This is your calling function. So first of all, y has a value, z have a function, z is a calling function, then return, that is add both y plus z values. This says, as I told you, procedure P computes y before calling to the Q. But it must also ensure that the value of y is available after Q returns. So this is after Q returns, this value will be used. This is Qy. So after evaluating or after analyzing or after calculating the value, it is stored to the y and then add y plus z. So this is your calling function and qy is your call function. As I told you, this is written. It can store the value of y in its own stack frame before calling to the q. When q returns, the procedure p can retrieve the value of y from the stack. In other words, p is the caller, saves the value, and y is the calling function that stores the qy. Then next is your examples, but before this let's take some stack overview again. There are some stack overview in PPTs. So starting with stack overview, this is finished, this is pending. Stack data structure. As I told you, stack is means LIFO, that is last in first out. So it is an array-like data structure. Array-like means whenever we collect or whenever we store more than one data, that is known as array-like data structure in the memory. In in the memory in which we can store the data, or we can store the data and remove from the location known as the top of the stack. As I told you, we can remove the data from the top of the stack, that is your LIFO, that is last in first out. So stack is an array-like data structure in which data can be stored and removed from a location known as top of the stack. So this follows LIFO, that is last in first out, means whatever items come last will be removed first. And the process of inserting is known as push, and process of removing is known as pop. This is the data that needs to be stored is pushed, as I told you, into the stack, and data to be retrieved means removed is popped out from the stack. So one is your pushed in and another one is your popped out from the stack. Stack is a LIFO data structure, that is last in first out. That is the data stored first is retrieved last. So that stored first is retrieved always last, that is last in first out. Assembly language provides two instructions for the stack operation, that is your push and pop. Push means inserting the data and pop means removing the data. Then next line says these instructions have syntaxes like push operand, pop address register. These are the syntax for push and pop. Next says the memory space that is used for stack segment is used for implementing the stack. There are two registers that is used for stack implementation, that is SS and ESP, or simply SP, that are used for implementing the stack, that is SS or SP. The top of the stack, which points to the last data item inserted into the stack, is pointed to by the SS ESP registers. Means the item which have to be removed is decided or done by the last item that is inserted is pointed by the SS ESP register. Where the SS register points to the beginning of the stack segment. Beginning means starting of the stack segment, and SP gives the offset into the stack segment. So this is your SS that indicates the beginning, and ESP means that gives the offset. Offset means the operations into the stack segment. Next is the stack implementation has the following characteristics. Till now we have covered how we can use the stack implementation. Now, what are the features of the stack implementation? First one is only words or double words could be saved into the stack, not a byte. This is your main feature, that only a word or either double words can be stored into a stack, not a byte. The stack grows in the reverse direction towards the lower memory address, because this follows LIFO. So this follows, or this grows in reverse direction, that is towards the lower memory location. So first of all, that data will be stored at the upper end, then below till lower memory locations or lower memory enters. Then next is the top of the stack points to the last item inserted in the stack. Because it is last in first out, so the top will be used as the last item inserted in the stack. It points to the lower byte of the last byte or last word insert. As we discussed about storing the values before using for some use, it can be done in the following way. First of all, this is your save the AX and BX register into the stack. So this is the stack implementation. First of all, save, that is push the AX and BX register. So push AX, push BX. Use the register for other purposes, means use the register for storing the values. So for, use move, because it is used for copying the data. So value 1, this is your source, this is transferred to the AX like this. First of all, push means insert in the stack. Now put the value of 1 to the AX, put the value of 2 to the BX. Till now clear? Next, move AX value to the value 1, BX value to the value 2. Then restore the original value means remove the value. So first task is to insert the values, then assign the values to AX and BX, then assign the AX value, that is the AX and BX value, to the new value, that is value 1 and value 2. Then at last delete the value or retrieve the value, that is pop AX and pop BX. So this contains 4 parts. First of all, insert the values into the stack, then move the value from value 1 to AX and BX, then move the value from AX BX to value 1, value 2, then pop the value, that is remove the values. Next is your same stack. Information for each function invocation. Example, link register is saved on the core stack or simply stack. Each function has its own stack frame. That is your stack frame, means each function have your own address in the stack. This is function 1, this is function 2, this is your stack frame, this is your stack pointer, this is your low address, this is your high address. So this is the diagram for the stack. Functions are stored, there is a stack frame, there is a stack pointer, there is a low address and the high address. How to use the stack? There is a main function, that is your v1, function 2, v1, function, this is your question mark. So there are two functions used, function 2, function, this is your function 2, function. It describes the stack and LR contains right shift and so on, multiple operations. Then what goes into the stack frame? Link register, parameters, return values, what else? So this frame contains 4 parts: link registers, passing parameters, return values, and the what else conditions. These are the contents of the stack frames. Now, next topic is your procedure examples. Till now we have covered what is procedures, what is stack implementation, what is the caller, what is the calling. Now, it's a time to take on or to look on the examples of procedures. So let's start. First of all, take 5 to 10 minutes break and then come back and then started with procedure examples. Next topic. So let's take 5 to 10 minutes break, then come back. Now let's start with next topic, that is your procedure examples or your procedure examples. As an example, consider the C function defined in figure 23, where function caller, that is your calling function, includes a call to function swap add, means first of all swap and then add the values. Figure 24 shows the stack frame structure both just before the caller call swap and while the caller ends the caller is running. Some of the instructions access stack locations and relative to the stack pointer, that is ESP, while other access locations relative to the base pointer, that is EBP. These offsets are defined by the lines. Now let's see with the help of coding how we can access, how we can take the data. This is your first example. Int swap add means swapping means interchanging the values and then add the values. This is your function name. Which function name? This is your function name. Then this is your return type. These are the arguments. So I'm writing this is your return type. These are the arguments. These are the arguments, right? And this is your function name. Right? Then this is return type, this is argument, this is function name. Then int x equals to pointer, that is star xp. int y equals to pointer yp. Means using two new variables, that is x and y, and stores the value of xp and yp. Now swap the values. Y value is going to the xp because xp has a value x, or x has a value xp. Now put the value of y to xp and x to yp. Now values are swiped or values are swapped, means interchange, then return x plus y, means then add the values. So first of all take the function, then use it two variable, that is x and y, and uses xp and the yp for storing the values in x and y. Then swap the values, means x become y and y become x, and then at last add the values and return the output. Add the values means adding the values of x and y, and then returns the output that is done by the return statement. In the same way, this is done using the C language. Now, next part is your how we can use by using the caller function. This is your int caller. Int argument 1 equals to 534. Means argument 1, arg1 equals to 534. arg1 is a variable that stores the value, or that stores the digit 534. Then there is argument 2 that stores 1057. Now in sum is your another variable that takes swap at argument 1 and argument 2. So argument 1 and argument 2 that contains 534 and 1057. This adds the value and put the output in sum. Next, difference equals to argument 1 minus argument 2. Means first of all find out the difference, then return sum into difference. Sum value, first of all addition, that is your 534 and 1057. So that is your 1591 into difference. Difference is minus this is, so 1037 minus 534. This is your 310. This is your 5. This is 5. 2, 5. So multiply 1591 into 523. So that is written by the function. This is how we can use the function. This is example of procedure definition and code. So this is your function definition. This is your function code. Next, the same arguments, how it is stored in stack, that can be represented by this figure. First of all, argument 1, argument 2, this is your unsaved data, this is your argument 1, argument 2. This is your save, that is ampersand EBP, just before call to swap add. This is your frame pointer, this is your another stack in body of swap add, this is your argument 1, argument 2, this is your unsaved, same address, this is your return address. This is how we can implement, or how we can store in by using the stack pointer, by using the stack values. Now next example is your using the push and the pop. This is passing parameter to a functions. First of all, there is a caller that is push1 ampersand EBP, that is save old. Old means the previous value in the EBP, that is ampersand EBP. Then moves the EBP value to the ESP. Set EBP as a frame pointer. Then allocates 24 bytes on the stack. That is your sub1 24 ESP, means uses the ESP value to the 24, or set the ESP value to the 24. Then move 1, that is 534 minus 4 EBP, means move the values of EBP to the 534. Then next move L, that is move the EBP value to the 1057. That is set argument equals to 534, set argument 2 equals to 1057. Now compute ampersand, that is ampersand argument 2, that is done by comparing, or LEAL, that is load address, load effective address, by computing or compute ARG2. Then move 1 EAX 4 ESP, that is store on the stack, then compute ARG1, store on the stack, and then call the swap function. This is how we can push and the pop and move and the call the swap function. This is another example: swap add, swap EBP, ESP, EBP, EBX. Now, next is your pop function. This is the code for swap add. Move EDX to the EBP, get XP value, get YP value, get X, get Y, store Y at XP, store X at YP, then return X plus Y. So these are the code that is used for adding the two numbers after the swapping. Then there is a pop, restore the EBX and restore the EBP. Then there is a return statement. So this is how we can done. This is your first part. This is your first part. There is a caller function. Then there is a push function. This is the push function. Then there is a body of the swap add. Then there is a pop function. Then there is a leave and the return function. This is the example how we can use the push and the pop and the procedure for adding or for subtracting. Means how we can use the procedures in assembly language programs. This is another practice problem. Now, next topic is your recursive procedures. Till now, we have finished with the simple procedure. Now, next topic is your recursive procedures. Recursive means describing or calling same function again and again. Or if I call a function, that it called a function again and again to itself, that is known as recursive. So, first of all, let's take the PPT. What is recursive function? First of all, introduction. A recursive procedure or the recursive function calls itself. Means it will call itself either directly or indirectly. Now, there are two parts. How we can call either directly or indirectly. Indirect recursion, a procedure calls itself directly. Means a procedure calls itself directly. In indirect, procedure P makes a call to procedure Q, Q in turn calls to procedure P. Means by default P calls itself, but indirectly P goes to the Q, Q goes to the P. But the main target or the main result is that P calls P. But here in indirect, there is a mediator between the P, that is P goes to Q and Q goes to the P. So there are two types of recursion. First of all, what is recursion? Simple. When a function calls itself, when a function invoke itself, that is known as recursion. There are two types of recursion. One is direct, one is indirect. Indirect procedure, the function calls directly, that is P calls to the itself P. But in indirect, P calls to the procedure Q, Q calls to the procedure P. The sequence of calls could be longer before a call is made to P. Because in indirect there are multiple procedures, because P goes to P, Q goes to P. So there are two procedures. Next is recursion is a powerful tool that allows us to express our solution elegantly. Some solutions can be naturally expressed using recursion. Computing a factorial is a classic example. This is your best example for showing the recursion. Factorial is denoted by n factorial. It is the product of positive numbers from n 1 to n. For example, 5 factorial. This is from 1 to n. N is a 5. 1 into 2 into 3 into 4 into 5. That is, it calls itself, that is known as factorial, or that is known as recursive or factorial of a function. Next is, the factorial can be defined as factorial 0 equals to 1. Means at the 0th location, the value is 1. Another location, the value is, this is the most important, factorial n equals to n. This is your number, that is 5. 5 into factorial n minus 1 means 5 into factorial 4, like this one. First of all, I have to find the factorial. So factorial 0 equals to 1. So this is a value 1. Then factorial n. Suppose I have factorial 5. So equals to 5, that is n into factorial, that is fact 5 minus 1, that is your 4. This is n minus 1, that is 4. So this is 5 into factorial 4, that is your 4 factorial. In the same way, next time it calls itself, that is your recursive function. Next time it becomes 4 into 3 factorial. Then it becomes 3 into 2 factorial. Then it becomes 2 into 1 factorial. Then it becomes 1 factorial into 0. This is how we can call itself, or the procedure call itself, that is known as recursive function. Recursion shows up in this definition as we define factorial n in terms of factorial n minus 1. Every recursive function should have a termination condition. There is a termination condition to end the recursion. In this example, when n equals to 0, that is, when n becomes 0, the recursion stops, because the condition is that n is greater than 0. So when the n is 0, that is, when the number reaches to the 0, then the recursion stops. So the condition is that n is greater than n is greater than 0, not equals to, but only greater than 0. Next, how do we express such recursive functions in programming languages? Let's first look how this function is written in C. Now let's see how it is written in C language. This is the function name, that is factorial. This is your argument, that is your n. This is your condition. If n equals to 0, return once. Means if n equals to 0, then display nothing. Simply return the one value, that is return the 0. That is your garbage value or any grammatical or any error on the screen. Then next is, if this is not equal to 0, then return n into fact n minus 1. In the same way, this is n into fact n minus 1. As I told you, first of all 5 into 4, 5 into 4 factorial, then 4 into 3 factorial, and so on till 0 when the condition is true. Means this is a C program. This simply says take one variable n. If that n is 0, means if that digit or that number is 0, then display nothing. Else calculate the factorial by using n into fact n minus 1. So first of all, if the example is 5. So 5 into factorial, 5 minus 1, that is 4. So that is 5 into 4 factorial. Then in next iteration, 4 into 3 factorial. Next iteration, 3 into 2 factorial. Next, 2 into 1 factorial. These are the multiple recursions which we have to use whenever we have to calculate the factorial using recursion function or using recursion procedure. So this is how we can call and how we can return. This is your calling function. This is n equals to 3, factorial 3 equals to 6. As I told you, factorial 3 into factorial 2. Now factorial 2 has a value 2. This is 2 into factorial 1. This is 1 into factorial 0. Factorial 0 equals to 1. So this is how we can jump from here to here. First of all, calling. This is calling. When n equals to 3, this is your output. 2 output, 1 output, 0 output. Now this has a value 1. Recursion terminate. Now gives the value, that is your return statement. 0 has a value 1. 1 has a value 1, 2 has a value 2, 3 has a value 6. So this is how we can calculate. So the output is 6. This is activation record for D, activation record for C, activation record for B, activation record for A. So this is first of all 3, 2, 1, 0. This is your output, 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 goes from bottom to top. This is your values. 1, 2, 6. This is the recursion function, how it will be implemented using the programming code, using the assembly language, or using the C language. Next topic is, what are the problems that are facing or that we face whenever we use the recursion function. But before this, let's take your book, a review of your book. This is your recursive procedure. This says when a function call itself or call themselves, that is known as recursive function. The stack discipline naturally provides the proper policy for allocating when the procedure is called. Means when a procedure is called, a memory will be allocated, and when the procedure is deleted or procedure is return something, then it deallocates the memory. This is the example, same example, int rfact, that is finding the factorial. There is one argument, that is int n, result. If n is greater than equals to 1, result is 1. Means if n is greater than or equals to 1, result is 1. Otherwise, find the factorial, the same example. Find the factorial n into rfact n minus 1. Only the name of the function, name of the procedure is different. Their name is fact, here name is rfact, that is recursive factorial. This is the syntax for how we can use using the stack, that is LIFO. This is your stack frame for recursive function. First of all n minus 1, then saved EBP, EBX, EBP, then there is a stock frame for calling procedures. So this is the array implementation, this is the recursive function that we use in assembly language. Now, next is your, what are the problems that is available in recursion function? Means what are the problems that we face while using the recursion? So there are two types of problems. One is inefficiency, then another one is increased memory requirement. So first one is your inefficiency. This says in most cases recursive versions tends to be inefficient. You can see this point by comparing the recursive and iteration version of the factorial function. The recursive version includes more overheads, means it takes more resources, more overheads to invoke and return from procedure call. So this says the one of the problem is that it is inefficient because the recursive uses more overheads or require more overheads to invoke and return, to call and return the procedure calls. To compute n factorial, we need to call the factorial function about n times. As I told you, result equals to n into fact n minus 1. Means every time it calls itself. So this takes lots of overhead to invoke and return from the procedure calls. In the iterative version, the loop iterates about n times. So whenever there are 5 digits, so it will iterate 5 times. 10 digits, it will iterate 10 times. This is inefficient. This is not efficient while using the coding. While using the big program or the large program where there is a 10,000 lines of coding. This also introduced duplicate computation. For example, to compute the Fibonacci FIB Fibonacci 5, that is 4 plus 3, that is 3 plus 2 twice, and so on. So this will be twice, multiple times the same function. Then the next problem with recursion is that it increases the memory requirement. Whenever we store the values using recursion, so this needs a lot of memory or increase the memory requirement in the coding part. So this says recursion tends to demand more memory. As there are more variables, more computing work, so this demands more memory. This can be seen from simple factorial example. For large n, the demand for stack memory can be excessive. Means whenever we use n, the demand for the stack memory increases because I have to find out the factorial of n. So the demand or the requirement for the stack memory will increases automatically. In some cases, the limit on the available memory may take the recursive version unusable. Means there is no use of memory, but if I am using recursive function, so this takes a memory, so that is your increased memory requirement. So this leads to the wastage of the memory. So there are two problems. One is your inefficiency, another one is your increased memory requirement. These are the two problems that we are facing while using the recursion function. Now, this is your example. This is same example of the factorial example. So the first line says the recursive definition of the factorial is, first of all, 0 factorial has a value 1, n factorial has a value n into n minus 1 factorial. Note that n minus 1 factorial equals to n minus 1 factorial into n minus 2 factorial. So if there is n factorial, that is n into n minus 1 means minus 1 values. This is n minus 1 minus 1 value, that is n minus 1 minus 1, that is n minus 2. So for n equals to 3, this is 3 into 2 as I told you. This is 2 into 1, this is 1 into 0 factorial, and 0 factorial equals to 1 by default or by definition. This is the example for the factorial, how we can use the factorial multiple times. Next is your example, how we can implement with the use of C coding or C++ coding. This is your code, int fact, that is factorial int n. This is your function name, fact, another in argument, in parenthesis there is a argument, that is n. If n is greater than equals to 1, means if n is greater than equals to 1, not 0, but 1 or above 1, means 1 or either more than 1, then return 1, else if there is n equals to 0 or greater than 1, then return the 1 simple, because this is 0, then return 1, else return n into fact n minus 1. Same procedure, 5 into 4 factorial, 4 into 3 factorial, 3 into 2 factorial, 2 into 1 factorial, 1 into 0 factorial. This is the recursive case result. This is your base case result. Then void main void cout fact3. This example says 3 values, that is n equals to 3, that is cout, that is print fact3. So whenever we use this function, this will jump the cursor like this. This will jump the cursor to this. So this is your calling function, this becomes your calling function, and this becomes your call function. So this is known as CALL caller, and this is your CALL double E, that is your caller. So this is your caller, where we can from where we can invoke the function, and this is the definition of the function. Next is your code in assembly language. This is your example. This is the code in C language or C++. This is your code in assembly language. First one is code, then fact, procedure, near, C, n, did word, that is double word. This is your syntax, this is your comments, in fact, intent. If n is greater than equals to 1, then move 1 to the EAX. EAX is your register, else move n to ECX. That is, if n is greater than equals to 1, this is result return 1. This is put 1 into EAX and then finish. Else put n to ECX, so that we can find return n into factorial n minus 1. This is your decrement, that is decrement ECX value every time. So this n is stored in ECX. Now decrement the value of ECX one by one. That is 5 become 4, 4 become 3, 3 become 2, 2 become 1, and 1 becomes 0. Next, invoke fact ECX, means invoking the value of factorial and stores the value of ECX to the fact. Then multiply, that is mul, and then end if. This is your if, starting if, this is your ending if. This is your fact, factorial function. Return, this is your return value, and this is your end if. This is your main function, this is your main function. This is how we can implement the recursive function in assembly language. So prior slide, this slide shows the basic example. This is your coding example. This is your assembly language coding example. This is how we can implement the coding assembly language program. So that's all for today's session. Now let's take a quick review or the quick recap of the today's class, that is what we have covered in the today's class. In today's class, I have started with the topic procedures, that is what is procedure, how we can use the procedure, how we can invoke the procedures. So procedure is nothing but it is a collection of instructions that we can use for writing the code. That is known as procedure. This is the syntax for procedure. There is a procedure name, procedure body, and there is a return type. That syntax, procedure are of two types. One is your intra-segment, another one is your inter-segment. Intra-segment means whenever we are using two procedures, that both two procedures are stored on the same memory, that is your intra-segment. And inter-segment means both the operands or both the operators or both the files, both the values are stored on different memory locations, that is your inter-segment. And then we have covered what are the parts of a procedure, that is declaration, coding, return, termination. This is your move, this is your example for returning, this is your end of procedure, that is end P. Then these are the multiple procedure implementation, how we can implement the procedure, either using ABI, that is application binary interfaces, calling conventions, recursive functions as I discussed, and then examples. So these are the most important for writing reusable, that we can use again and again, and maintainable code, so that it can be maintained very easily whenever we use assembly language program. These are the general concepts. There is a caller, there is a calling. Then we also studied what is the stack, how we can use the stack, what are the terms used in the stack data structure. So there are two terms used, that is push and the pop, and that stack follows FIFO, that is last in, first out, that is the data stored first is retrieved last. There are two operations, push and pop. These are the syntaxes for push and pop. There is a memory location, memory space, the stack follows following features. It uses words and double quotes rather than bytes. This is the example how we can use the stack. First of all, push the values, then move the values, then retrieve the values. This is the stack diagram, how we can implement the stack. We also studied how we can implement this, what is the syntax in the, or what goes in the stack frame. Then we also studied what is the register usage convention, means what are the registers we can use while using the assembly language program. What are the types of registers we can use There are two types of registers that divide into two categories, that is your caller save, that is your callee save. There are multiple registers like R0, R3, R12, LR, CTR. There is a callee save, that is R14, CR24. Next, we also study what is a recursive procedure. Means the same procedure calls itself, that is known as recursive procedure, that can be done either directly or indirectly. So whenever a function calls itself or the procedure calls itself, that is known as direct recursion. And suppose one function, one procedure calls another procedure, and in turn another procedure calls the same procedure, the original one, that is known as indirect. Suppose P goes to the Q, Q in turn goes to the P. So by default P calls itself, but in indirect way. That is an indirect recursion. The best example for in the recursion is finding a factorial. Suppose I have to find the factorial for 5, so that can be done by using the recursion function. This is the syntax for recursion function. This is the example or coding for recursion function. The condition is that n, that is the digit, is greater than 0 but not equals to 0. This is the syntax how we can use. This is the example of 3. So this will operate, or this will iterate in 4 parts, that is 3, 2, 1, 0, and then output will be stored, that is 1, 1, 2 and 6. So 3 have a factorial, or 3 factorial have a value 6. These are the multiple problems that we are facing while using the recursion function. One of the problem is that there is inefficiency, means it is not efficient. Sometimes it gives duplicate results, sometimes it uses more overheads to return and invoke the procedure. Then next limitation or the next problem is that it increases the memory requirement. So whenever we have to store more data, duplicate data, so that needs more memory requirement. So that is, it needs or it increases the memory requirement, and it is one of the limitation of recursion function. These are the example. This is the basic example, factorial example. This is the coding example. Then there is the assembly language code example. So that's all for today's session. Thank you so much everyone. Now if you have any doubts, then please text the doubts and I will answer you. In tomorrow's class, the topic will be array allocation and access, and the next topic, that is your 9th topic. So that's all for today's session. Now if you have any doubt, then please text the doubt and I will answer you. Okay, thank you so much everyone.